Hey guys, welcome to this video. So in this video, we're going to talk about one of the variation of the gradient descent. So gradient descent already I've talked about in the previous video, in particular the batch gradient descent. So here we're going to talk about the stochastic gradient descent. And so what is actually the difference between the batch gradient descent and the stochastic gradient descent? Is that in the stochastic gradient descent, as the name suggests, it's basically the meaning of the stochastic is basically the random. And how this random is important to this kind of a technique is that unlike the batch gradient descent where we treat the whole training data, we do all the mathematical changes and the gradient update with respect to total training data, whereas in case of the stochastic gradient descent we actually use a random sample of training data, random sample of training data, and we calculate the gradient out of it, gradient, and using that gradient we try to optimize the coefficients. And if you repeat this particular step for a large number of times, which we call actually as the epochs, then we will be ending up to a point where we have some coefs to the features which will ensure that we have the cost function minimized, cost function at minimum. But there is how we actually do it, how we actually minimize this cost function in with the respective gradient descent is by what we do is we, let's say if we plot the cost function, and just like the batch gradient descent, we start with some random value of the coefficients, and we take a steps to come down. But this is actually the actual variation of the batch gradient descent. But in case of the stochastic gradient descent, we randomly choose some of the data points, and that's why this kind of steps are not actually regular. The stochastic gradient descent is basically very irregular. That means the steps what we see, it will be more like we are actually kind of, we are drunk and we try to do some come down like this and stuff like that. So this kind of a feature, this kind of a feature will be very much evident with respect to the stochastic gradient descent. Now, there is one actually benefit of having this kind of a irregular update of the coefficients is that, let's say we have a cost function which is not so much convex. We have some of the troughs, we have some of the peaks, and something like this. So if we have this kind of a irregular update or bouncing kind of a cost function minimization, there is a high chance that we might able to come out of this local minimum and then finally reach the global minimum. So this is one of the advantage in case of the stochastic gradient descent, because our the way the cost function is minimized, it's bouncy in nature, and that's why we're able to come out of this local minimums. But there is also a downside that if you are always bouncing, there is a high potential that you will never reach the global minimum. Instead, you will be bouncing around like this. So the solution to that, the solution to the bouncy nature is by optimizing the learning rate, optimizing the learning rate with respect to the time steps, right? So in the previous, in the batch gradient descent, we already have fixed LR, right? We have a fixed learning rate. But in case of the stochastic gradient descent, we do not have a fixed LR. Where what we have is basically a, we call as a scheduler, learning rate scheduler. So and what it actually does is, with respect to the time steps, at how much what is the number of epochs, depending upon that, it will actually reduce the LR as we reach. So the LR will kind of get reduced as we actually move down. So this is the kind of a relation. So LR will go down, the learning rate will go down as the epochs go up. So this kind of a relation, inverse relation happens, and that is actually the solution to this kind of a nature where you want to avoid a suboptimal coefficient values, right? So what we'll try to do, we'll try to use the same code what we have written with respect to the batch gradient descent, and we'll see how we can implement the same thing with respect to the code in the stochastic gradient descent. And the theoretical part, let's jump to the the programming part, and we'll see how we can implement this in the code. So here I have the same code which I have written for the batch gradient descent. And what you're gonna do is you're gonna reuse some of the part of the existing code, and we're gonna build on top of it, right? So let's make a child class out of it. I'm gonna call it as the LR with stochastic gradient descent, and we need to call the parent class, right? So, and what we're gonna need is, like we have seen in the theoretical part, that we'll be needing some information about the epochs, number of epochs you want to run, right? So this we're gonna take as an parameter. Let me just quickly define this. It's epochs. And what you're gonna need also is that when you're gonna update the learning rate, we also need some of the time stamps, right? Or time stamps, what time stamps you're gonna update it. So let's call the initial timestamp as T naught, and this will be the initial timestamps you're gonna start with. Let's say we're gonna run all the way from the after we complete the fifth, or let's say 5 or 10th epoch till the last epoch. We're gonna reduce the learning rate, correct? And so this will be the T naught, and T1 will be the last timestamp or the epoch count when you're gonna update the learning rate. Right. So I have already implemented the fit model method inside the original batch gradient descent. So what I'm going to do, I'm going to override this function from the LR with SGT child function. Right? So fit model. Okay, so I do not need this. What I'm going to do is, so some parts we can actually reuse. So let's say I can actually use this till this point. Right? So the same thing that we gonna first take the x and y, we're gonna reshape them. Then you're gonna see how much of the samples we have. I mean the number of rows and also number of features. And what I'm gonna do, I'm gonna add a one column to store the my intercept values, and then I have this xb which is having both the features as well as the space for the intercept. Now from here we're gonna divert the implementation. How we gonna calculate this with respect to the HGT. So the first thing we're gonna do the um, let's store this into the variable here, and same goes with theta. Actually, we can copy this part also. Now from here, first what we're gonna do is we first gonna iterate through all the epochs. So let's say for epoch range all the epochs we have. So self epochs. And inside that each epoch, what you're gonna do, you're gonna take the random samples out of the training data. So for that, I'm gonna do something like I'm gonna pick out the indexes, row indexes, and the total number of rows. And then what you're gonna do, I'm gonna just select a random index. So NumPy will come handy. What we're gonna do is we're gonna take a random dot integer, because obviously we're dealing with the a random index, which will be an integer anyway, and we're gonna take a sample from x and y. So we have already defined the the x b, which is my x, I mean the x variable here, and the y. And I'm gonna do something like this, that I want um, random index plus one. Same goes with the y, where I'll take this. It's just a set of x and y for one sample. So you'll be having this one row of data where I have all the x values and the y values, corresponding y values to that x feature value. Done the x and y values for the ith sample. So now what do we need to do? We need to find out the gradient of that ith sample, right? So the gradient formula is basically same like what we have done in case of the batch gradient descent. It's just that in this case we have the whole data, in a whole training data we have been considering, whereas in this case it will be just the x and y for the ith sample, right? So we can actually rewrite this same expression, just that in case of here we have the m, which is basically the number of rows in the training data set, whereas in this case it's just a single sample. So it will be 2 by 1, which is basically just multiplying the whole array with just like with 2, scaling by 2. So we have xi dot transpose of it, and then dot product of xi dot product of theta minus of height. So this will give us the gradient of the ith sample considering the x and yi. And after this, we also need to consider the learning rate. The learning rate is basically not fixed as in the case of the batch gradient descent. So we need to define some kind of a function or some kind of a method in which we pass on the timestamps information, which is in this case will be the number of rows, the epoch number, and the the sample, how many samples we have. So let me just quickly define a method. We call it as learning scheduler, and we need to give some timestamp information, right? So what I'm gonna do is return the we have the initial information of the time, where the time timestamp plus some good. So now we call it as the art. Let's call it learning rate for I. That will be basically the we call the method running scheduler, and there we pass the of information into the n, which is in our case the number of rows plus row index, right? So we have calculated the learning rate for the ith sample. Now we're gonna update the theta. So we have theta, that is the theta minus the learning rate I, the gradient of I. So if you consider this, we loop over all of this thing for number of, I mean, that number of epochs. So finally, we have the theta, which is basically the updated version of the what we have initially started with, and we can actually use this particular line of code to get my intercept and the coefficients. Right. Cool. So here we have the define the the linear regression with the stochastic gradient descent. So let's do one thing. Let's try and compare with the same kind of a data set, and we'll see that how much the coefficients are getting different from what you have seen with respect to the uh, linear regression in the sklearn, the batch gradient descent we have implemented earlier, and now with the stochastic gradient descent. So let me just rerun this. Okay. Sklearn. So this is basically what we get from the sklearn's implementation, and this is what we have done in the last video. We have got this kind of a coefficient, and let me just quickly run this object to pass the box. We go with 100. T starting let me give as 10, and T1 let me give as 100. Right now, let's fit the model. Our model is trained. Let me quickly see this coefficients and the. So as you can see, the coefficients of the first features is like minus 1.0213, and here we're getting minus 94, and the variables or the coefficient values are quite same, which is evident that whatever we are doing with respect to the stochastic gradient descent is very similar to what batch gradient descent does. Now, to have a quantitative comparison with the performance, what we can do, we can run the same kind of a, we can run the same thing with the test data set, and let's see what happens. So this is the output we get with respect to the sklearn's implementation. This we already have shown in the last video. We are getting around 16% of mean absolute percentage error, and R2 score is 66. So let me just quickly get the. So here, my you can see the quantity performance are very much similar to each other, and even though we have reduced the number of steps, the model is basically iterating. Hence, we are decreasing the total time taken, the runtime, but still we are getting the same kind of a performance. And even the attribution to the features are also very similar. Hence, we can actually use the SGT whenever we encounter situation in which have a very large data set. And I hope by this video you have got a very good understanding of how things work, the theory behind that, and also the the coding aspect of it. So do share this video with your friends, family, and whoever is interested, and please put your comments down below. Thank you.